to the second talk. I believe this is a joint talk by Colleen and Victor. They are from VMware. So let me just briefly introduce Colleen. So Colleen Josephson is a senior research scientist at VMware and an assistant professor at UC Santa Cruz. Her research interests include wireless communication and sensing systems with a focus on technologies to enable and improve sustainable practices. She completed her PhD from Stanford, and her other degrees are from MIT. Okay, I think we are ready, and please go ahead, Colleen.
Do you want to introduce Victor too? Because he'll be taking over halfway through.
Okay, so let me also, Victor is a research director at VMware academic program and leading research engagements with academic research groups and fostering collaboration with internal research teams and product group in the areas of networking, distributed systems, performance, and sustainability. He is the recipient of ACMC.com and SIG Mobile Test of Time Award. And I think last but not least, he received his PhD from UMass Amherst. Okay, go ahead.
Thanks. All right, so as we hinted, this talk has two halves. In the first half, I'll be exploring the concepts of energy curtailment and how we can leverage software to make use of that stranded energy. And in the second half, Victor will dive into some specific approaches and their challenges. So without further ado, let's talk a little bit about energy in the US. So this plot from the EPA shows how emissions are divided across sectors here. The three biggest contributors, which account for about 75% of all our emissions, are transportation, electricity generation, and industry, kind of vague. So where do we fit in? Our broader ICT industry? Well, a 2021 study found that ICT accounts for 2 to 4% of the globe's emissions. By some estimates, that actually means that our industry has higher emissions than the entire aviation industry. But that still might not seem like much compared to, say, the automotive industry. However, we do have to consider that our technology infrastructure is growing more demanding. We want faster speeds, higher resolutions, more dense sensor networks. So projections show that the emissions of our industry are expected to grow as much as 400% in the next 20 years. And this means that our modest 2 to 4% is expected to grow 10 to 20% without substantial preventative action. So awareness of this potential impact is starting to grow. Emissions cutting is a socially responsible thing to do. It's also something that people in industry are putting pressure on us to do. So our customers are very interested in this problem. So we know that our goal is 100% renewably powered data centers, but where are we now? So most of the energy we get for data centers comes from the primary electricity grid, and not all electricity is made equal. So we see here in this plot that grids are supplied by a wide variety of power generation techniques. Gas, hydro, coal, solar. So 100% renewable energy right now is the exception, not the norm. So it's important to see also that these figures aren't fixed. The sources of power the sources that power comes from, they fluctuate regularly, especially for renewables. So the supplies of renewables differ by region. You might have more wind in coastal regions, for example. And even within a region, the supply is going to differ based on time because the sun doesn't always shine and the wind changes directions. So this means that the carbon intensity of the electricity that we use differs across time. So in short, because we can't control when the wind blows or when the sun shines, the most straightforward solution might be to store power generated via renewables so we can use it on demand when needed. But this is challenging right now because the key technologies like sustainable batteries are not yet affordable at scale. Another challenge is that renewable energy generation is highly distributed. Our current infrastructure was built around more centralized generation. The distributed nature of renewables, this is exciting and interesting because it provides ample opportunity for innovation in areas like microgrids. But it also means that to convert to a 100% renewable grid, we have to invest in expensive and time-consuming grid modernizations. None of this is insurmountable. In fact, to quote Mark Jacobson, who's at Stanford University, this transition to 100% renewable energy is a solvable problem. But he also added in the very next sentence that it's more realistic to get to 80% renewable by 2030 and then hopefully get to 100% soon after. So if we're optimistically at least a decade out from being able to run all our data centers on renewable power, how can we make progress in the meantime? Due to the urgency of the situation, it's clear that we can't just wait for the grid to modernize and for battery technology to improve. Cutting emissions is too important to throw the problem over the fence. So what we need to do is look at how we can use software to ease the transition to 100% renewables. There's a lot of possibilities here, but our particular key idea is that if you move the compute and not the green energy. As we've been discussing, renewables are highly distributed, expensive to store, and though these problems are solvable in the long term, it's going to take major updates to infrastructure and advances in battery technology. In comparison, however, computational workloads have been designed with flexibility in mind to provide resilience in the face of equipment failure. So let's leverage this pre-existing flexibility and move the workloads to where the green energy is. So in other words, place workloads in a carbon-aware fashion. So there's 2 degrees of freedom in workload placement, time and space. So first, we'll discuss moving workloads in time. So here's a historical record of emissions in the Netherlands from a company called WattTime. The emissions are measured as marginal operating emissions rate, or MOER. It has units of pounds of emissions per megawatt hour. We see a highly diurnal, in this case, pattern, likely corresponding with periods of solar energy during daytime. Different grids are going to look very different, but each region tends to exhibit a repeating pattern that we can leverage. Computing has been very much dominated by an on-demand mindset, but not all jobs are made equal. So for example, if you have audio video streaming, that's highly latency sensitive, where batch video processing or training a machine learning model are far less time sensitive. So what we do then is identify time and sensitive workloads and defer execution to lower emissions periods. A critical component of this will be predicting these low emissions periods. As we saw in the chart on the previous slide, in many cases, this tends to be quite periodic, but it differs from grid to grid. And right now, another challenge is that the quality of data available for each grid is all over the place. Some record emissions on an hourly basis, other in 5-minute intervals. And the timeliness is a factor too. Some might have data available near real time, where others would batch upload it on a monthly basis for public record after the fact. So the wide variety of the quality of the data and the timeliness of the data is a challenge. So a takeaway is, as data from grids improve, our capacity to do these predictions is also going to improve. So we tested out this idea of shifting execution in time, and we found that even very basic forms of this process can easily save you 10% in emissions. We created a candidate workload of machine learning training. On the top in purple is marginal emissions rate for the grid supplying this particular data center. On the bottom is a plot comparing naive execution, purple, versus carbon-aware execution in pink. We see that the carbon-aware execution has lower emissions compared to the naive workload. This is a simple idea that's a great low-hanging fruit for sustainability innovation. So to start with, we can have people manually tagging jobs with their time sensitivity when the task is created. But longer term, we would want techniques to automatically identify candidate workloads. So this covers the basic idea of shifting loads in time. Now for the space dimension. As discussed earlier, different regions have different emissions. So here, again, is an example of the emissions from 2 grids in Europe over the same time period. Ireland is in blue and Netherlands is in orange. And we see that as the day progresses, across the two regions, there are a number of times where the carbon footprint of one is notably higher than the other for extended periods. So we can leverage this to load balance workloads based on carbon. So this is a great opportunity to lower emissions for more time-sensitive workloads. So instead of deferring execution for hours, start the execution when needed, but keep an eye on opportunities to relocate it to regions with more green power available. So walking through this, let's say we have a data center A and B with comparable carbon outputs. So if carbon A is the anticipated carbon load of completing the job at data center A, and carbon B is the anticipated carbon load of completing it at data center B, we also want to know the moving cost, which is the carbon cost associated with migrating the workload, which is probably a fixed value, and it's going to depend on the type of workload, whether it's compute heavy, data heavy, and so on. So if we want to move the workload, we want the overall cost of carbon to be moving the load to be less than the cost of staying. So this is the core idea. Obviously, it's a big simplification. We only want to move the workload if the threshold, the benefit is above some sort of threshold. And we also need to be monitoring the history of the workload to see if it's already been moved so we don't have flip-flapping. But the general idea is pretty simple. Do the computation where the power is more green. And this is a great opportunity because playing with this concept in our products, we pulled in emissions data for two US locations, Atlanta and Dallas. This is our vRealize operations dashboard. On the top is emissions for two locations. Atlanta is pink and Dallas is green. We see a number of times where one region has a notably higher carbon intensity than the other. Now the bottom half, and I apologize for the axes being the same colors, but the bottom half shows carbon aware, the benefits of the carbon aware workload placement. So pink down here is business as usual, where green shows emissions if we shift the workloads between the data centers to minimize carbon emissions. But this is really kind of early stage and conceptual in nature. We drew the data from real data center workload power profiles and real carbon intensity statistics over time for our actual power grids. In these idealized calculations, we estimate that we can cut emissions 10%, sometimes as much as 50% in different periods. So now we've talked about moving workloads in time and space. So let's look at the possibilities when we can do both. Curtailment, as we've heard, is the deliberate reduction in power output to balance energy supply and demand, or it can be due to transmission constraints. Renewables are difficult to curtail. If the wind keeps blowing, the turbine keeps generating power. So this plot on the right shows a renewable curtailment event in California in 2018. The solar generation exceeded the capacity of the grid or the supply and demand, and this power was simply not accepted. The lack of sustainable storage means that right now we often have to just dump the power or potentially cause issues with the grid. And the frequency of curtailment events for renewable energy is rising. So this means that we're leaving zero emissions energy on the table. So obviously it's undesirable to be discarding this renewable energy. So can we somehow take advantage of it? Curtailment conditions tend to last 1 to 2 hours, which fortunately is ample opportunity to spin up some of these time-insensitive workloads that we were talking about. The job might not complete, but that's okay. We can checkpoint it and finish it later. The core idea here is that we opportunistically increase the demand on the grid to take advantage of these curtailment periods so that every drop of green energy can get used. So our vision is that the product will receive notice of curtailment events and dispatch time-insensitive workloads to leverage this excess energy, which will be lower in cost and more sustainable than business as usual. So I'd like to invite my colleague, Victor, to take over for the second half of the talk.
Thank you, Colleen. Definitely available energy clean energy that is wasted is not good. So we really want to do something about that. And I've heard quite a few talks before, and literature starts increasing. But we need to look at moving workloads as the obvious response to the the flexible way to respond to this variable available of clean energy. So let's take a look at what are the challenges of moving this workload. So let's start with I would say the simpler case, which is Intra cloud provider. So basically an enterprise has some workloads uploaded in a cloud provider zone A, and then they decide to move it to another zone B. Next. So the problem, okay, so let's see what are the potential challenges here. So first of all, physical. What is the actual delay? Obviously bandwidth. Because this is all intra-cloud, usually the cloud providers have big pipes, and the workload migration would not have much friction. Delay might be low or medium. The cost might be low or none, depending on the cloud provider. And so moreover, compatibility would not be also a problem, because the enterprise deals essentially with the exact same cloud provider. So now, of course, and also that there are not much of security and confidentiality, provided that you trust the cloud provider. So if you trust cloud provider in zone A, you might as well trust cloud provider in zone B. Of course, there are some concerns. For example, if these are government customers and they have a concern about country borders, and of course you can still move things between workloads between zones within the same borders. So in general, all this, the challenges here, just using the same cloud provider might be, let's just say, manageable. Let's go to the next one, which is inter-cloud providers. So let's assume that the same enterprise has some contracts with different cloud providers, and they actually want to migrate the workload between these two. So next, obviously now we have some maybe that's fine. So now we have some physical challenges, and especially I would like to emphasize, we can talk about this a lot of time, but the famous cost of exporting data from one cloud to and bring it to another is many times quite high. And of course, encouraging enterprise to keep their data within the same provider. So that's a significant barrier. Compatibility might also be an issue with APIs being different. I'll talk about this on the next slide. Security and confidentiality is like, it's a mixed. So if you trust both cloud provider A and B, then the security and confidentiality may be not an issue. But of course, the enterprise now might have some responsibility in transferring between one and the second. So let's take a look a little bit more detail into what are the challenges next. So the physical challenges, obviously, you have data and code, and what do you do about that? So the naive approach is to just move everything from cloud A to cloud B, but there might be a better way to do this. Next. I would say, pre-positioning data and code might be a solution. Obviously, you put things, the bulk of all the data and code go in both cloud provider and B, and then you just move the state change, I would say, the delta. So that saves you on the cost, it saves you on time, delay. But of course there are cons. You do a duplicate effort, and it's a little complex to sync the states of this running workload. Now, you can also place the workloads, basically just assume that you're not moving, you're just making one decision, and based on some future casting of available green energy, and you say, I'm not gonna go to cloud provider A just for an hour because I know it's gonna be a whole day or maybe half a day available for cloud 2. I'll just wait for an hour and then just have it there. Of course, this works if you have some time Slack, available in your SLA, the service level agreement for that workload. And of course, if the workload takes less time, then there is available green energy there. So it's a limited, it's like a trade-off here. Next. So on compatibility, I'll just want to say just a few words about how can we tackle, because I just want to draw attention to some ongoing research. So APIs, how do you talk to the different services, and then the protocols, really networking stack. Next. So on each of them, there are a significant amount of work that has been done or is going on, and just wanted to underscore, besides the compatibility protocols that or APIs that are already there, like the S3 that is across multiple cloud providers. There is also this Sky Computing initiative, and you have some, if you would like to look for more, I have some recent publications that you can, look for more details. It's a lot of work there. Just to say that the intention here is to have some kind of a cloud provider agnostic shim layer or interface, so that all the enterprises with the customers would actually talk in one voice, and then they could choose whatever cloud provider there is, and that shim layer will translate into the provider's particular interface. There is also the extensible internet, which is the version of this compatibility layer built into the stack. In particular, it's a 3.5 layer, basically between the IP layer, the routing layer, and the transport layer. I'm gonna move on because the interest of time. Next slide, please. Okay, so here's the something that is really, how should I say, daring, which is cooperative computing. So some enterprises that have their own on-prem data centers might actually band together and do their own kind of inter-enterprise cloud and sharing, resources. I call this the return of the peer-to-peer. So next, let's see what the challenges are. Obviously, the physical, of course, there might be a physical, but I don't think that cost might be an issue here because they cooperate. There is compatibility, but they could choose similar protocols. I think the main concern here is this security and confidentiality. And that's my last pitch here on the next slide. What do we do about security and confidentiality? Next slide, Colleen, please. Okay, so there are many things that are going on. It's an emerging field, confidential computing. I just want to say a few words on trusted execution. There is, from the foundation, from the hardware side, the Intel, AMD you see here. There is also ARM. Everybody's doing this compartmentalization and basically keeping data not being viewed by others and not being able to alter it as well. There is, you can go up the stack with encrypted VM memory, secure memory mapping, and then the hypervisors, the one that manage the virtual machines. Based on these hardware extensions, they will be able to give you confidential VMs, containers, or enclave. Next. So there is two other things that are really interesting, but maybe for specific use. Homomorphic encryption, that's a really neat idea that's been for a few years now, where you can actually do computation on encrypted data without decrypting it. I find this very interesting and promising. Multi-party computation is the obvious, fragmenting data and code so that no single place understands what's going on, but then when they're reconstituted in results, only the customer, the end user, will get the unobscured results. And I have some further reading there. I think I'm done, Colleen. Next. Back to you, Colleen.
Thanks, Victor. So just a quick summary that carbon-aware computing seeks to minimize emissions without sacrificing performance needs. And to make workloads carbon-aware, we can migrate them in time or geography to help overcome fundamental challenges in renewable grids. So workload migration opens systems and network and security challenges. There's a lot of emerging and ongoing research. So we leave with kind of a call to action, set goals. A lot of people, it's a good mix here of industry and academia. Do you have a research or product idea to improve sustainability? Make it this goal part of your work. Spread awareness. So pick facts or ideas from today's workshop and bring it back to the world. Discuss it with a colleague who wasn't here or a friend. Build partnerships, so be a force multiplier by collaborating with academic or industrial colleagues on sustainable computing products or projects. And finally, continue to research emerging topics such as cooperative and confidential computing. So with that, we are complete, and I know we're short on time, but we could maybe take a couple of questions.
Thank you so much again, Colleen and Victor. It was a great talk. Yes, we are running out of time, but if there are some quick questions, feel free to unmute yourself and ask.
Hi, Victor and Colleen. I have one question. So, yeah, thank you for call to action. And there is a lot of work on some of the aspects of this sustainable computing that you mentioned. But what do you see are the major challenges in applying all of this academic research into action? And do you have anything sort of specific projects that are already underway at VMware that are basically helping out the actual consumers of or the users of your cloud or products?
I'll let Victor speak on the academic challenges, but I can talk a little bit about the products. We do have a number of features in a number of products that are either there or being beta tested or under development. We're very active in this area right now. It's one of our priorities for the upcoming year. That said, it's a personal goal for us to try and make people more aware of these features that either exist or are under development, because I think a lot of people don't realize that they're around and know how to use them. And so, Victor, maybe you can talk about the research, integrating research aspect.
Absolutely. Thanks for the question, Mohammad. I mentioned on purpose the two initiatives on the previous slide on sky computing and extensible internet. We are founding members of that initiative, and research and development groups at VMware work directly with the academics at Berkeley and other universities on those two initiatives. Moreover, I also put a pointer to the Confidential Computing Consortium, which is again, VMware is again a founding member, and that is a consortium between university and academia. So I invite everybody to take a look at that and be active there as well.
Philip?
Yeah, thanks a lot. I was wondering, you talked a lot about flexible tasks and migrating them in time or between data centers, but how would you go about identifying these tasks? Do you expect the users to provide information about deadlines or stuff like that? Or
yeah, so I think we're viewing it as kind of a ladder approach, where you start off with users tagging things that are flexible we recognize that that's not ideal. So it's kind of an active area of research to figure out how do you automatically identify these candidates who are suitable for the type of movement that we're talking about. So it's kind of it's a very open question.
Okay, cool. Thank you.
So why not leave these tasks to application and just provide them flexibility to move? Like applications can decide themselves if they want to move or not, and where they want to move or not. Or do you think more of it as a system level solution that the cloud operators or the intermediate managers should be managing?
That's a great question. So I think, and one question is, how does the application get insight into these conditions? So there certainly is a middle layer of information passing that we would have to expose, especially if they're working on kind of our multi-cloud suite of products. Yeah, the application is going to have the best insight into whether or not it wants to be moved, but there needs to be some way to pass that information. So maybe our role is kind of creating the API to allow people to move things around. Victor, did you have anything to add to that?
Of course, it's the energy hypervisor developed at UMass. And we are looking forward to and we are looking forward to using that as soon as it is available. Working together and the collaboration is the key. Whether it's our programs or projects or anybody else's, the collaboration is key.